Hey everyone, in this video, I'm going to go over the AATC Chem 118B Worksheet 2. So I'm going to go over the concepts of the worksheet first, and then I'm going to go over the practice problems of the worksheet. So first, let's go over the reactions of alkenes hydrogenation, which is when we are given an alkene with H2PDC, we are going to reduce this alkene by adding hydrogens to it on the same side of the carbons of the alkene, which is called a syn addition. So in this case, we added 2 hydrogens, 1 for each carbon on the same side, which means that in this case, since the hydrogens are being added to the planar side, the other groups would have to be wedges or dashes. So we know that the methyl group and ethyl group are on the same side, which means that there would both be dashes here. And we see that these two methyl groups are on opposite sides of each other, which means that there would be opposite sides of each other here. So one of the methyl groups here would be dashed, the other methyl group would be wedged. And to redraw this, we could redraw this in a way that this methyl group is on the opposite side as that methyl group, and this methyl group is the same side as that ethyl group right there. And since all of these are single bonds, all these sigma bonds would have free rotation and change orientation as well. So next, let's go over the reactions of alkenes, where we react an alkene with a nucleophilic acid like HBr, HCr, HCl, or HI. So let's go over the mechanism here. For this mechanisms, you would want to form the more stable carbocation. In this case, we could either form a secondary carbocation or a tertiary carbocation. Since we want to form the tertiary carbocation, since it's more stable, we would have to grab the hydrogen on the other side of the carbon, on the less substituted side, and kick out the good leaving group, bromine. After that, our double bond is broken. We have a hydrogen bond to the less substituted side. And since this carbon lost the bond, it has a positive charge now, carbocation. And whenever we form a carbocation intermediate, we always look out for a rearrangement like a hydride shift or methyl shift. In this case, we don't have any carbocation rearrangements because we are earning the most stable form, which is this tertiary position. Then we bring in our bromine minus group that just left and attack that carbocation, giving us our final product. And that is basically the Markovnikov rule, where the hydrogen would add to the least substituted side, giving us the more stable carbocation intermediate. Then let's go over the electrophilic hydration of alkenes. Whenever we're given an alkene and acid with water and heat, then we know that we're going to hydrate the alkene by adding alcohol. So let's go over the mechanism here. We're going to do the Markovnikov rule again. We want to form the more stable carbocation, which would either be this carbon or this carbon, the secondary carbocation or the tertiary carbocation. Since the tertiary carbocation is more stable, we are going to grab the hydrogen from the less substituted side and form our carbocation in the more stable position here. Then we bring in our weak nucleophile water and attack that carbocation. Since there's no carbocation shifts, we could just skip to the step over here where the water attacks that carbocation. Then we do a deprotonation step to deprotonate this positively charged oxygen here of the water group that just got added. Now let's go over the practice problems of the worksheet. So whenever you see D2 PT, think of D2 as an isotope of H2. So the reason why they draw D2 is because they want you to draw explicitly the stereochemistry of the deuterium ion. So we know that the hydrogenation is a syn addition, and to avoid steric hindrance, since these two bulky tert-butyl groups are wedges, we're going to add the deuterium as dashes to avoid steric hindrance. Syn addition. And now for the next one, we have hydrogenation again, 2 alkenes. So we're going to have this product over here. And for this alkene here, if we add the hydrogens on the same sides, then we would have this structure where these two carbons here are not chiral centers because they don't have 4 different unique groups. This first carbon here has 2 methyl groups, which makes it not a chiral center. The other carbon has 2 hydrogens, which also makes it achiral. But for the next alkene, we see that we do have 1 chiral center, which is this chiral center here. So we would have to account for that by including stereochemistry. So let's say that the hydrogen got attached as a hydrogen in the first product, but then as a wedge for the second product. Okay, and then now we could determine the R or S of this chiral center here. For the first chiral center, we see that these 2 carbons are the same CH2, CH2. So we look at the next carbons. These carbons are also the same CH2, CH2. And now we see the next atom, which is this oxygen, which takes priority over the carbon because it has a higher atomic number. So this would be our priority number 1, priority number 2, and then our priority number 3, CH3. And this is our R chiral center here. And we don't have to invert it or do any changes because our hydrogen, the lowest priority group, is already on the backside. And let's do the same for the other molecule. So it looks like R, but since the hydrogen is, wait, I gotta draw a different product here. So this methyl is gonna be dashed. This hydrogen is gonna be wedged. Since it looks R, it's actually going to be S because we have to flip the thing it looks like since the hydrogen is on the wedge. And that only works if the hydrogen is on the wedge. It wouldn't work if hydrogen is on the planar side. So this would be S here. Okay, now let's go over to the next problem here, where we have an alkene and a nucleophilic acid, HI. So I'm going to go over the mechanism of this to explain why we would have 2 different products. Okay, so think of the carbons of the alkene as a nucleophile because there's a lot of electrons close to each other, making it negatively charged. So let's say we could either form a secondary carbocation here or a secondary carbocation here. They're both similarly stable. So that's why we would have 2 different products. Where if this carbon here grabs the hydrogen, we would form a carbocation on that side, where the nucleophile iodine will attack there, give us this product here. Okay, but let's say that the other carbon instead grab the hydrogen of the HI, kicks out the iodine there, then we would form the carbocation on the other carbon, where the iodine can then attack that carbocation, giving us our second product here. Okay. So we would have 2 products here, which is this and this. Okay. So now we're going to go over the hydration of alkenes, where we have an acid, non-nucleophilic acid like H2SO4, and water and heat. So I'm going to go over the mechanism of this as well. 1, 2, 3, 4, 5, 6 carbons. Okay. 2, 3, 4, 5, 6. Water and heat. So we want to form the more stable carbocation here, which is the Markov-Markov rule, which is the secondary carbocation, which means that this carbon here, the less substituted carbon, would get protonated by the acid, H2SO4. Then that forms our more stable carbocation here, which then our weak nucleophile water can then attack. Since it's a carbocation, the water can either attack on the top side, giving us a wedge product, or the bottom side, giving us a dash product. So I'm going to indicate that by just doing a planar addition here. But this planar addition means that this water group could have been in the wedged side or the dashed side. Then the very last step here would just to reform our acid catalyst and deprotonate this positively charged oxygen, giving us our product. Okay. And now let's go over the nucleophilic acid reaction again with the alkene. We see here that we have an acid, an alkene. We want to form the more stable carbocation, which is this carbocation. That means that we're going to have to protonate the less substituted carbon. Then that gives us this carbocation intermediate. We look out for any carbocation rearrangements like a hydride shift or methyl shift. In this case, we don't need to worry about that because it's in its most stable state. Then our bromine leaving group that just left will be attacking that carbocation, giving us our product. Where these two methyl groups here of the product are these two methyl groups here. Okay. Now let's go over the same reaction again. But in this case, there's different reaction going on in the mechanism as well. So we have a nucleophilic acid and an alkene. We want to form the more stable carbocation, which is this carbon here. That means that we're going to protonate the less substituted carbon, which is going to be this carbon, kick out the leaving group iodine. That gives us the secondary carbocation here. Then we see that this cyclobutane is a very unstable. We could form a more stable 5-membered ring. So I'm going to label these carbons 1, 2, 3, 4, 5, where the 5th carbon is the carbocation. I'm going to break the bond between carbons 1 and 4 and form the bond between 4 and 5. Then that would give us this 5-membered ring. 1, 2, 3, 4, 5. Then we see what's attached to each carbon. We see at carbon 5, there's a methyl group. And at carbon 1, there's also a methyl group. Since carbon 4 and 5, since carbon 4 still has 4 bonds, and carbon 5 gained a bond, carbon 5 is now neutral, but carbon 1 lost a bond. So that makes carbon 1 positively charged, making it carbocation. Then the iodine that left from the first step here will be able to attack that carbocation, giving us our final product here. Okay, now let's move on to the next part. We want to fill in the missing starting materials or reagents. We see that our reagents here are H2SO4, water, and heat, which indicates a hydration reaction from an alkene, where the alcohol is at this carbon. So that means that our alkene could have came from one of these alkenes here. And since the pink and green alkene are the same, since they're both methyl groups, we would only have to draw one of them. So our reagents here would be the alkene and this alkene here. I didn't draw out the green alkene because that would be similar to the pink alkene here. Okay. And now we have to fill in the reagents here. We see that these two groups are on the same side as each other. They have both dashes, which means that the hydrogens here are both wedges. And the reaction that adds hydrogen on the same sides in addition to an alkene is hydrogenation, H2PDC. Okay, now let's go over the next problem, which is the mechanism problem. We see here that we have H2SO4, 2 water or excess with heat, which is a hydration reaction. And since we have 2 alkenes, we added 2 alcohols here. So first, let's go over the top alkene here. We want to form the more stable carbocation, which is going to be this tertiary carbocation rather than the secondary carbocation. So we're going to protonate the less substituted carbon here. That would give us this tertiary carbocation, where one of the weak nucleophilic waters, will attack that carbocation. Giving us this intermediate here. Then we would neutralize this positively charged oxygen with another water base, neutralize that oxygen. And for these mechanism problems, we would have to be detailed on all the steps here. We can't skip any steps. Like you can't go from this carbocation to this neutral alcohol. You would have to also show the neutralization step where we deprotonated this oxygen here. Okay, and now let's do the same thing for the other alkene. We see that we could either form a primary carbocation or a tertiary carbocation. Since the tertiary carbocation is more stable, we're going to protonate the less substituted carbon, which is the primary carbon here, to form the more stable tertiary carbocation. That gives us, let's say, OH. Okay. And then now we could bring in our other weak nucleophilic water to attack that carbocation. And that would give us OH. Okay. Then this water here with the positively charged oxygen, because this is the water group that attacked. And to neutralize this oxygen here, we would have to deprotonate the oxygen with, let's say, another water molecule. And neutralize this oxygen here, giving us our final product here.